we started seeing the quasi-free electron model, and I give you some results. I mean, I derived some consequences in the case of the one-dimensional system. So I just would like to remind you. So this is what we saw last time concerning the quasi-free electron model, or the quasi-free electrons in one dimension. So in one dimension, we started from the free electron in the ghost lattice. So for the energy as a function of k, we knew we could focus just on the spectrum inside the Brillouin zone. So from minus pi over a to pi over a. The energy in the free electron case, but using Bloch theorem, was epsilon of k is equal to h bar square over 2m k plus n times 2 pi over a square. This is where the energy En for the band n, and we had seen that the periodic part of the Bloch state in the free electron case in the ghost lattice was un of x is equal to 1 over the square root of a. This comes from the normalization exponential I n 2 pi over ax. So for the free electron in the ghost lattice, this is the periodic part of the Bloch states for any n integral. And so we had seen that the band structure one obtains is the start of the parabolic band of the free electron here for n equal to 0. And then the folding of this continuation of the band, because the spectrum, energy spectrum must remain the same from that of the free electron. So this, when it's translated by 2 pi over a, gives a band like this, which corresponds to the n equal 1 here. And then the continuation here of the free electron band, when translated by plus 2 pi over a, this was minus 2 pi over a, gives a band like this. Oops, okay, it crosses at the same point. And this is the n equal to minus 1 in this energy dispersion. And then, of course, there are other bands that appear for higher n, which are all the possible, all the foldings of the free electron band, which has to be with the same energy spectrum as the free electron, but inside the Brillouin zone, because we use the Bloch theorem, and we know that all eigenstate can be written as Bloch state with k inside the Brillouin zone. So this is what we saw starting from the free electron, and then we discussed the perturbation to the first order, the effect of the perturbation to the first order on this spectrum. So the perturbation is of the type in one dimension minus v1 exponential I 2 pi over ax plus exponential minus I 2 pi over ax divided by 2. So the cosine of 2 pi over ax. This is the perturbation, and when we saw that when we evaluate the matrix element n, so this is my state n. Here, when we evaluate the average value of the perturbation on the state n, so v n, I will call it v1, we obtain 0. This means that if we consider a state, a key point inside the Brien zone, not at the zone center and not at the zone edge. So in the case where the spectrum at the 0 order is non-degenerate, we have no degeneracy, and when one calculates, for instance, for this state, which corresponds to n equal to 0 here, the matrix element is 0, and for any of these cases here, there will be a change with respect to the 0 order eigenvalue to the first order in V, in the perturbations. That's what we saw. And we also saw that when one looks at the case where there are degeneracies, for instance, here and here, then if one calculates, for instance, here the matrix element between these two states of the perturbation, so for instance at pi over a, at the key point pi over a, if one calculates, the diagonal elements will be 0, so 0, 0 and 1, 1 will give 0 mean value for the perturbation. But if one calculates the off-diagonal matrix element, so between the two relevant states here, that give a degeneracy, that are degenerate, one obtains, so this is the complex conjugate of this. Yes, no, that's correct. This gives us, as we saw last time, V1 over 2. And therefore, one has to diagonalize to get the first order correction. A matrix of the type 0 minus V1 over 2 minus V1 over 2, 0. And this gives us the first order corrections at this K point, at the Brien zone edge. And these corrections are plus or minus V1 over 2. So this means we will have here a splitting between the state that were degenerate before, and this is a splitting by V1. So at the zone edge, the perturbation is going to remove the degeneracy. So the degeneracy is removed considering the first order correction at the Brien zone edge. So that's what we saw last time. Now, so the consequence is that at the Brien zone edge here, these two eigenvalues which are degenerate will split in one eigenvalue here and another one here, with a separation here V1. This is the splitting. So we will have this as eigenvalue at the Brillouin zone edge. Now I would like to discuss the validity of the first order perturbation correction in this spectrum, for this spectrum. So, I mean, what one knows from first order perturbation theory is that the amplitude of the perturbation should be rather small compared to the zero order eigenvalue. This is something that for sure should be satisfied in order to have a first order correction that gives us the main result. Yes? Oh, sorry. But it's not all that what is required actually. So here I'm discussing what is needed for the first order correction to be close to the exact result or final result. So it's for a non-degenerate state, it's useful to also have a look at what would be the second order correction in the energies. So in the case of non-degenerate state, for non-degenerate states, the second order correction order correction is delta AI, so this is to the second order. This is equal to the sum of all over all the G indexes corresponding to the other zero order eigenstates. So J different from I. I'm summing here over the zero order eigenstate except the one for which I want the second order correction. So, and then here in the numerator, one has the matrix element J, V, 1, well, V, I square over the difference between the zero order eigenvalues. So E0I minus E0J. This is the second order correction in perturbation theory for non-degenerate states. So obviously, in order for the second order correction to be small, one needs to have this denominator being large with respect to the matrix element here. So if one is well inside the center of the Brillouin zone, if I want the correction to the second order due to all of these other eigenstates, so the other states here, it's okay because the difference in energy between this state and this state, the reference state here, and this state is large. So, the denominator for the n equal 0 eigenvalue here will be large, and in this case my correction will be small. But of course, if one goes close to the Brillouin zone edge, this becomes, the denominator becomes smaller and smaller and starts to vanish. So there is a problem, of course, here, because the second order correction becomes important. And that's why the first order correction here is not sufficient, because we know it's 0. And actually, the correct result would be a continuation with respect to what we find at the Brillouin zone edge. So, in reality, you will have a band which will behave like this if one includes also higher order correction for the states which are close to the edge of the Brillouin zone. Okay? So here, basically, the result is sufficient to the first order, and the band structure is like in the free electron case, but close to the Brillouin zone edge or close to the generacy. To the generacies, one has to be careful, and there, when there is a splitting, essentially near the splitting, there is a continuation of the band to the result of the free electron inside the Brillouin zone. So my continuation here is that the separation between the eigenstate Aj0 minus Ai0 must be larger than the perturbation matrix element so the numerator, in the numerator GVI for the first order correction to be sufficient. So for non-degenerate correction, the second order correction is this, and the separation must be larger than the perturbation matrix element VGA for the first order correction to be sufficient. So this implies that close to plus or minus pi over A. Okay, equal. The first order correction is not sufficient. It's not enough. Finish my sentence for first order to be. So for the first order to be enough, one has to have a large difference here, and if it's not the case, then one should go to higher order. All right, here I wanted to keep the drawing. Another thing I wanted to discuss. So this is the first thing, that is this energy difference, so the separation for a non-degenerate state to the other one should be sufficiently large for the first order correction to be enough. Now, another necessary condition to have at the first order valid result is that the perturbation matrix element should be small. The perturbation should be small compared to the energies obtained to the zero order. So another condition that should be fulfilled is that the matrix element of V should be small compared to the typical bandwidth, which we know from last time. At this point, the energy is h bar square over 2m times pi over a square. This is the energy here. So the matrix element of the potential V should be rather small compared to this typical energy. So the typical expectation value values of this matrix element JVI, which are of the order of the absolute value of V1 in our one-dimensional example, these must be much smaller than the typical unperturbed eigenvalues. And these typical unperturbed eigenvalues, so the bandwidth, are of the order of h bar square over 2m pi over a square. And this, I can rewrite it as h bar square over 2m A0 square, where A0 is the Bohr radius, times pi over A divided by A0 square. Square. I just multiplied and divided by the same thing. So A0 is the Bohr radius. And this is typically, well, this is equal to 0.529 angstrom. So it's essentially half an angstrom. And the A here in a typical metal is around 3 angstrom. And this is the Rydberg, h bar over 2m A0 square, and the Rydberg, it's 13.6058 eV. This is the Rydberg. So here I have something of the order of 10, and this object here, given A is around 3, this is typically of the order of 0.1 to 1 for physical A. This is typically the order of this pi over A divided by 80 squared. So in the end, the whole thing is of the order of 1 to 10 eV. These bands are of the order of 1 to 10 EVs. So the perturbation matrix element, or V1, have to be smaller than that for the first order correction to be valid. And in a metal, this is typically the case. So this is the second condition for the first order correction to hold. Okay? So that's it for this part on the one-dimension quasi-electron model. Any question? Everything clear? Okay, so now I'm going to give you some homework for next time. 2 problems. So the first one is actually a problem that was given as a problem for the midterm test many years ago. And the second one is a bit tougher, and is a problem that it would be closer to a final exam problem, but the last part is actually pretty tough, so it was never given as a final exam. Okay, so homework for next week. Two problems, and that will allow you to practice quasi-free electron model. So the first problem is in one dimension, and basically it is to examine, to analyze what's happening at this point. At the Briançon center we have also a degeneracy. So the first question is to evaluate similarly as what we did at K or at the Briançon edge. Evaluate similarly the splitting at gamma, which is the Briançon center, for the two degenerate state. So the degenerate states corresponding to n equal plus and minus 1. These are the two states that become for the two U states for which in the free electron the eigenvalues are the same. So to evaluate the matrix element and the correction to the first order using the perturbation that was used for the splitting of the Briançon edge. Let's see what is the splitting in this case. And then this is a little bit less precise, but to discuss the conditions for the presence of a splitting, for the presence of a non-vanishing splitting. Well, this of course is related to what you will find in the first, from the first part. One asks you to discuss what is needed for a splitting. So that's one problem. The second problem is in 2 dimensions. Quasi-free electron in 2 dimensions, and in the case of a square lattice, now we can remove that. And so if I look in the reciprocal space for a square lattice, kx, ky, so my lattice point will be 0, 2 pi over a, minus 2 pi over a, and so on. So this is the square, the reciprocal of the square lattice, and my Brillouin zone will be like this. The square. So this is the Brillouin zone. And we will call the Brillouin zone center the gamma point. And this point here will be called x, the x point, and this point here will be called the m point. So we will ask you to calculate some band structure along some high symmetry lines in this 2-dimensional Brillouin zone. So the first question is to generate the G vectors with a norm smaller or equal to square root of 2 times 2 pi over A. So this is to generate all the 0 order eigenstate for the free electron in the ghost lattice, the 0 order U functions for this Rave lattice. And then for the free electron in this ghost lattice, we will ask you to plot the bands along the gamma x direction. For a free electron in a ghost lattice, the first thing will be to plot, calculate and then plot the bands along the gamma x direction. For up to an energy epsilon smaller or equal to 2 times h bar square over 2m 2 pi over a square. So to plot the bands for energy up to this energy. And then to plot also the bands along, so this is along this direction, and then also along this direction, gamma m. So to plot the bands along gamma m, and this with energy up to smaller or equal to h bar square over 2m 2 pi over a square. So up to those energy. This is the first part. And then we will give you a perturbation potential, and we will ask you to calculate some splitting that are found in these bands. So the next part will be to evaluate the effect of a perturbation of the type V1 cos 2 pi over a x plus Vi cos 2 pi over a y. This is the perturbation. So to evaluate the effect of this perturbation on the lowest degenerate state at x, on the lowest degenerate states at x and also at m. So after you have drawn the bands, you will just look at the first case where you have the degenerate state at x and also at m, and evaluate for these two cases the effect of this perturbation on the degenerate levels. And then this is the part that is more complicated. Some question or it's
the first condition, generate the g vectors with square root of 2. It's by capital G we mean the allowed momentum of free particles.
Yeah, the G, this is the reciprocal space. So the vector of the reciprocal space for the square lattice, you just should enumerate them.
Yes.
And see how many, group them by degeneracy, by norm. With increasing norm up to this. This is going to give the perturbation afterwards. Well, the basis, I mean, the states that are relevant for calculating the matrix element in perturbation theory. So now, this is more difficult for 2 electrons per cell, and assuming that the perturbation V1 is small, and small v, the question is the system an insulator? Well, okay, this part is still can be done without too much problem, but actually it's the next one. If not, discuss the shape of the Fermi surface. Discuss the shape of the Fermi surface. Well, this sort of implies that the answer to the first question is not no. Well, the second part is a bit more tricky. The last question is a bit more tricky, but okay. We will distribute the correction afterwards. I mean. All right, so this is for the homework. No, you need to exercise and try to solve them, and then you will have the corrections. Well, the first one we probably will discuss it briefly in class, and the second one, which is more lengthy, I will distribute the answers. And, but it's in your advantage to try to solve it, of course, first. Okay, so that's it for the homework. So now I would like to discuss the consequences of the quasi-free electron model, and I will anticipate also the result of the second problem. Okay, so let me erase first this. Okay. So this was kind of parenthesis, the homework. Now I'm continuing the course, and I want to mention some consequences of the quasi-free electron model of what we saw. Consequences. Well, so this is still in the quasi-free electron model part of the course. So consequences for systems with one electron per unit cell, and this I already anticipated. So for a system with one electron per unit cell, for instance, sodium, potassium, which all crystallize in BCC structure. This corresponds to half-filled band systems. we have seen from the quasi-free electron model that there is no first order correction for the relevant valence state. The field state and the Fermi energy are well inside the Brillouin zone, close to the Brillouin zone center, and therefore in this region it's safe. The first order correction is valid, and we saw that it's exactly zero, and therefore these systems behave like free electron. So these are basically free electron systems. Their properties, electronic properties, are well described by the free electron model. Okay? So this is for one electron per unit cell. Now, for 2 electrons per unit cell, from the quasi-free electron model, we can expect main qualitative changes near the Fermi energy. Main qualitative changes near the Fermi energy. Because we saw that in those cases the perturbation with respect to a constant potential will induce splitting, and it will induce splitting in region, for states that are important to describe the physical property of the system, the states near the Fermi energy. So the perturbation in those cases will open. The perturbation will open gaps. And the physical properties will be significantly affected with respect to the free electron model. Physical properties will be significantly affected. So in those cases, for 2 electrons per unit cell, we expect major changes with respect to the free electron systems. So in those cases we expect qualitatively major changes with respect to the free electron system. So in one dimension, basically it open, the perturbation, the periodic perturbation will open gap at the Brillouin zone edges, and it will make the system an insulator in one dimension. Now, in 2 dimension and in 3 dimension, actually, it's not going to be sufficient to make the system an insulator. The system will be bad metals, that is, metals with a low density of state at the Fermi energy. So, in the case of the real system that have 2 valence electron per unit cell, like calcium and magnesium, for instance, in reality, in nature, in the 3-dimensional case, these are weak metals, bad metals. And in general, in 3D and in 2D, these systems are weak metals, also in 2D. Whereas in 1D, as we saw, the perturbation will induce an overall gap, and the system will be insulator. So the question for you is why? Yes, can someone guess why there is this difference? In one dimension, it's in, when one introduces a periodic perturbation, it's going to produce a splitting at the Brillouin zone edge, and as a consequence, there will be an overall gap in the system. That is, at any K point in the Brillouin zone, there will be an energy separation between the field state and the empty states. Why is it actually not so in the 2-dimensional case? Can someone? Yes.
I would guess because of the dimension M, where there is x and ky relatively close to each other.
What do you mean?
In the plot, you brought it just a little bit in the exercise.
Yeah.
There is the diagonal direction.
Yeah.
When the distance between the x and y are a little bit close, not like the distance between the x and the next x.
You mean between the center and the edge?
The diagonal.
Yes, the distance goes. You can achieve larger k vectors inside the Brillouin zone. That's what you mean? Going along the diagonal? Probably, yeah. I think you see it right. So let's see. Okay. The reason. So, the reason is that the splitting occur in places where there are degeneracies in the free electron model. So these degeneracies occur actually always at special points, k points, never at an arbitrary k point inside the Brillouin zone. In situation where there is no high symmetry. So typically they occur at the Brillouin zone edges, the degeneracies and the splitting. Now, in the two-dimensional case, in the square lattice, for instance, we have seen the Brillouin zone. So, well, it's not a good drawing. So, the Brillouin zone is the x point and the m point. So, these are the k vector, kx, ky. And the free electron model gives us, if I look at the direction kx, so gamma x here, I will have a parabolic band. I mean, it's the free electron band, it's just h bar, the lowest band, and this is my Brillouin zone edge, the k point. Now, so this is epsilon, sorry, the band. And the splitting will occur in this region, and they will be of the order of V1, as we have seen, that is the perturbing potential. Now, if I look along this direction instead, the segment is larger, the length of the k point, and the energy goes like a constant, the norm of the k vector square. So here I'm going to go further in terms of length when I go to the m point from the gamma point, and my energy of the parabola will go to a higher value at the Brillouin zone edge. And there will be also some degeneracy. I mean, you will see it from the problem also that you will solve at home. And this splitting will be V1. So the splitting occurs here and here. But this is much higher in energy than this. And therefore, overall, for 2 electrons per unit cell, you have to fill
V1 or 2 V1 for the gamma M splitting?
It doesn't matter. Let's say it's V1. But it's small in any case. But in one dimension, it's enough to open a gap everywhere, in the sense these are the only points actually that separate the first band from the higher band. So in one dimension it's enough to lift this degeneracy to open a band gap everywhere, because that were the only points where you didn't have a gap. Now in 2 dimension, okay, you open a small separation here, a small separation here, but overall you have to have the Fermi energy, which is everywhere the same in the system, because it's extensive. It's an intensive, it's an intensive value, so it's thermodynamically everywhere the same. So you have a Fermi energy, and it's going to fill this band only partially, and this band more than it's actually going to start to fill the second band, because the Fermi energy will have to be in between to fill overall a band in the system. So basically, your splitting here will be below will be above the Fermi energy, and here below the Fermi energy. So in some places in between the 2k points, you will have the Fermi energy, which is really inside where the splitting occurs. So it's going to give a gap. But in several places, actually, this splitting will not create a gap at that k point. So that's why it will be metal still, because there are places where the Fermi energy will cut a band. But the splitting will help in some places in between the two, where, of course, the Fermi energy remains the same, but gradually this will move up when one moves from K to M, and in some places this splitting will help to make it less metallic. But it will still remain a metal, but a dead metal. Okay, more or less. That's the reason. Okay, I helped you for the second problem here. But that's a consequence of the quasi-free electron model.
Just to make clear, in this case, in 2D or 3D, the metal is insulator in some directions and conductor in several directions. Is that correct?
Yes, but being a metal, being an insulator means that everywhere
yes.
you should have, I mean, that there should be everywhere, well, there should be a separation between the highest occupied state and the lowest empty state. If at some point in the Brownian zone you have the Fermi energy crossing a band, this cannot happen because you will have a degeneracy between the highest occupied and the lowest empty state. So it will not be an insulator. It's a strict condition to be an insulator. But it will be a bad metal in the sense that the density of state at the Fermi energy will be small. In the limit where it's zero, it's an insulator. But it will be finite but small, so it's called a bad metal. Okay, now I would like to discuss a little bit more. This will make this also a bit more clear. The quasi-free electron approach for 3 dimension and for 2 dimension. And since it's easier to draw in 2 dimension, I will do the drawing in 2 dimension, but it can be generalized to 2 dimension, the conclusions. So now I'm going to discuss a bit more the 3D case and the 2D case for the quasi-free electron. So, okay, let's start from the free electron Bloch state. So the free electron Bloch state. So C is proportional to exponential kr times exponential I j r, where k belongs to the Brownian zone and j belongs to the reciprocal lattice. And my Hamiltonian, the zero order Hamiltonian, this time I take the full crystal Hamiltonian, is just the kinetic part that is with zero potential, so h bar square, gradient square over 2m. So this is the zero order Hamiltonian in the case of the free electron in a ghost like this. So the weak periodic potential, the difference with respect to the average value, will induce some splitting, and it will induce the splitting in the places where there are degeneracies in the for this Hamiltonian. So what we derived, the matrix element being 0, the average value being 0 for the free electron UN, is valid in 1 dimension, 2 dimension, and 3 dimension. It's the same argument and the same result. So it's only where there are degeneracies that we will obtain to the first order a splitting. So we have to look in places in the Brillouin zone where there are degeneracies for the free electron case. So the weak periodic potential will induce splittings. Where there are degeneracies. Where there are degenerate states of H0. Wrote it H0. Okay, so we have to look at places in the Brillouin zone where there are degeneracies. So one should look for K vectors where the energies are degenerate. So where the epsilon 0 of K are degenerate, that is, since the H0 is the free electron Hamiltonian, places where the vector K plus reciprocal lattice vector have the same norm. So we should have K vectors such that K plus G1, well, okay, with vectors K plus G1, K plus G2, and it depends on the order of the degeneracy, K plus Gn, are such that the energy is the same. So H bar square K plus G I square over 2m for all of this n, for all of this I equal 1 to n, have the same norm. So we are looking for k point or k vector such that there are some G vectors that give the same energy for the free electron case. So this implies that the norm of K plus G must be the same. This is the cases where there will be the degeneracy. So we, the condition of having a degeneracy is that for that K point there will be two or more G vectors such that K plus G give the same energy, meaning that the norm of K plus G must be the same for at least two different G vectors. And the corresponding function U will be 1 over the square root of omega exponential I G1 R omega exponential I Gn R. Okay, so basically these are the conditions for the degeneracy, and this will happen only at special K point in the Brownian zone. So in general, for an arbitrary K point in the Brownian zone, in the Brownian zone, there will be no degeneracy. This, it was clear in one dimension. The degeneracy will occurring only at the Brownian zone edge and in some cases at the Brownian zone center. But something similar is true in 2 and 3 dimensions. The degeneracies occur only at special K points. So I will draw things for the 2-dimensional case. And I will consider, as usual, the square lattice, where it will be rather obvious. So we consider the square lattice. So in the case of the square lattice, I have my points of the square lattice in reciprocal space. So these are the points. And I have my Brownian zone. Okay. This is the Brillouin zone. Now, it is clear that if I take an arbitrary point in the Brillouin zone, let's say here, if I look at the images, adding and subtracting G vectors, I will obtain, okay, so this is my K point. If I add some G vectors like this, I will obtain an image here. If I subtract, I will obtain an image here. If I continue, I will obtain an image here, an image here. I can obtain an image here also, and I will have an image here. So these are the images when I add some G vectors to this point, and you can not find any two couple that will have the same length if you take an arbitrary point in the Brillouin zone. All of these vectors have different length, so you will never find, there is no degeneracy in those cases. Now, if you take instead a point that is, for instance, on the Brillouin zone edge, like a point here, then if I subtract a G vector, I will obtain my point, an image here. And these two vectors have the same length, K and K plus G, so I have a degeneracy here. Okay? So if I take this type of point, K plus J, I will never have two vectors of same length. Whereas in the red case, I can find, I will have degeneracies. So I know that if I'm on the Brillouin zone edge, if I'm here, I will have degeneracies. The same applies to any point here. If I take a point here, this K point, and I subtract this G vector, I'm going here, and these two vectors have the same length, so anywhere on the Brillouin zone edge, I will have degeneracies. But that's not all. Actually, if I'm on this axis, I will have also degeneracies, because if I take a point, let's say here, if I add this G vector, I will obtain a point here. If I add this one, I will obtain a point here, and these two have the same length. So also this point will give me degeneracies. Okay?
Yeah.
Okay. All right. So if I'm here and here, I will have degeneracies. And actually also if I'm on the diagonal. Because if I take a point here, I can add this G vector, I will obtain a point here, and I can add this G vector and I will obtain a point here, and these two lengths are the same. So again, I will obtain, I can go down, okay. I have too many red points, but okay. I mean, this was for this one. I will obtain images that give me the same length. So all of these situation in red correspond to K point where they will be the genesis, and therefore one can find the genesis either at the Brillouin zone edge or at the Brillouin zone center or along high symmetry line of the Brillouin zone. These are the places where there are the genesis and where splitting may occur. So one can find the genesis at the Brillouin zone edges, at the Brillouin zone center, and along high symmetry lines. Of the Brillouin zone. So these are all the red points that I indicated, the red zones I indicated. So this is in 2 dimensions, but of course in 3 dimensions it's the same argument. It's always Brillouin zone edges and along high symmetry lines of the Brillouin zone that you can find K points where they are the genesis. That's where they are located. Okay, so now for if one is on one of these red points, so in the case when one has identified the regions of the Brillouin zone where they are the genesis, then one should take the G vectors that give this the genesis. So in the degenerate subspace, of the UN, one should diagonalize the matrix Vij this matrix. Well, in practice, what you will do when you start a problem of this type is that you first look at the G vectors and you order them by increasing length. So you have some shells of these G vectors that have all the same length, and you list them by increasing norm and how many G vectors you have in each cell. So this will be what you will use for your basis of the U. And then, if you have to look at the specific K point, you look at your G vector and you see going from the lowest norm to higher, which are the G vectors that give degeneracy in the K plus G. And you take the lowest of the norm K plus G, and you do this diagonalization in the degenerate subspace. So the first step is always to order the G vectors, because this will be your basis for the perturbation. Okay, so once you have this, and you have the lowest norm for the K plus J that gives you a degeneracy in your subspace of the degenerate function U. You will calculate the perturbation, and then, and this perturbation V of R, since the potential is periodic, it has the periodicity of the Bravais lattice, you can always expand it as a Fourier series. So you sum over the G vectors that belong to the reciprocal lattice. You have some coefficient P of G exponential I G R. So you can always write your crystal potential as a Fourier series this way, and then the only non-vanishing elements you will find are for the G vectors such that Gi plus Gj plus G is equal to 0. And in this case, the matrix element of the perturbation will be Vij is equal to 1 over omega, the integration of exponential minus I J I R times V tilde of J times exponential I J R times exponential I J G R cubed. So this is this matrix element using the Fourier expansion of the potential, but I know that I will have non-zero matrix element only when I have this conjugation fulfilled, and therefore here I will obtain V tilde of G equal to J I minus J G. So these matrix elements are very simple. They are just the Fourier coefficient of my potential for the G vectors that correspond to Gi minus Gj when the functions are Ui and Uj. Okay? These are the only matrix elements that, the Fourier coefficient give the matrix element, basically. So in the case where you have a two-dimensional degeneracy, twofold degeneracy, you will just diagonalize. So if you have a twofold degeneracy, like you will have in the problem you should solve at home, so for a specific K point, for instance on the Brillouin zone surface, if you have a twofold degeneracy, so the point norm of K is equal to the norm of K minus a specific reciprocal lattice vector G, then you will obtain a matrix and you have to diagonalize it, so have the determinant here of E0 minus epsilon P tilde of J1, the complex conjugate, you have to calculate the determinant, obtain the zeros, and this will give you the eigenvalues. So in 2 and 3 dimensions, you will have something similar to the one-dimensional case, where what will appear for the splitting are the Fourier coefficients of your crystal potential. Okay, well, I guess I will stop here, and I guess things will be more clear after having solved the problems. Any question?